Hello, this is Terry Kuzma here at Penn State University, and today we're going to look at bottom-up manufacturing. Specifically, we're in part two of our series, and what we're going to do today is look at adhesion properties. And the example that we're going to follow, we're actually going to look at uh, adhesion from nature, specifically the gecko foot. So let's take a look where we are. We're doing some definition and examples, and what we're looking at is material interface forces, and specifically today we're going to look at weak forces like van der Waals attractive forces. And again, the example that we're going to look at the most is from nature, and that's with the gecko. So the gecko foot hairs exhibit a form of adhesion due to van der Waal forces. This is a solid-solid interface mechanism. The mechanism of adhesion has been a topic of discussion for hundreds of years, but until moderately recently, people didn't really know how this animal was able to walk up walls, etc. So van der Waals forces, if we take a look at those, they're attractive forces between two neutral atoms or molecules. They actually, to operate, they need a low separation distance. And then the calculations, mathematical calculations, were developed in the 1950s. And we can take a look at these equations. So the macroscopic interaction energies are calculated by this equation with some familiar uh, constants that we're aware of, like Planck's constants. We had to measure the separation distance between the media, the frequency, and the point between two media. So we can actually calculate that number of energies that's associated with this van der Waals contact. Interestingly, when they did examine finally the gecko foot physically, and compared it to the calculations, the number worked out rather well. So it's actually proof that this mathematical concept in the 1950s was correct. So this is, again, the force. You can do the mathematics there in equations examples if you need to. So these are the constants defined in the equation that was worked on in the 1950s. So contact splitting, we're looking at what we're doing here, and again, this is, I guess, a tenet of nanotechnology. As we take an object and split it, make it smaller and smaller and smaller, different things happen. In this case, what we're looking at is fibrils or hairs on animals, and as we get these fibrils smaller, what physics changes for us. So contact splitting is adhesion will be improved on one surface when it's split into many small fibrils. The force required to separate two surfaces is based on the number of fibrils. So we can see the force is a function of, or a square of, the number of contacts that exist on the surface. So there's 5 reasons that this contact splitting occurs. We have strain energy. This propels separation and leads and must be released in every fibril, so that potential energy is there. Conformity, less energy is required for the fibrils than for a smooth surface. Because they can conform to the new object, so they can get close to exhibit these van der Waal forces. The ratio of the surface to energy loss from the distortion increases for smaller contacts. Again, this is an issue of contact. We get better contact with smaller fibrils. Uniform stress distribution occurs before fibrils can be removed. And this also limits the defect size. It reduces damage from a single defect because simply there's more contacts. So if one of those fails, we still have plenty of contacts to supply our force. So in the year 2000, some researchers in California looked at and identified the spatulae as providing the adhesion forces. The sheer abundance and the proximity of the surface of these spatulae make it sufficient for van der Waal forces alone to provide the required strength. So this is FESEM pictures of the gecko foot taken from the American scientist, and we can take a look at the macro structures, and then the mesostructures, and then the microstructures, and then finally the nanostructures on those hairs. So as we look at it, we can see that these things, under an FESEM, etc., we can see the detail of them. So this bottom one with the many nanostructures on here, this has the ability to be conformal to the surface, and it also has the ability to integrate a tremendous amount of nano forces or van der Waals forces over an area, and the integration of that small forces over a large area gives us actually a large force of adhesion. So the feet of a gecko are covered with elastic hairs called setae, and the end of these hairs are split into nanoscale structures called spatulae. I hope that's how you pronounce them. I think it is. The underside of the gecko toe are covered with uniform ranks of setae, with each setae further divided in hundreds of split ends and flat tips called spatulae. The single setae of the tokay gecko is roughly 110 microns long and 4.2 micrometers wide. Again, this setae is on the order of what a human hair is. So on average, a human hair is approximately, there's different sizes of hair, etc., but a hair is around 100 microns, and visually we can see down to about 30 microns. So 4.2 microns wide, we can't resolve that with our eyes. So each setae branches ends into thin triangular spatulae connected to its apex. The end is about 0.2 microns in length and 0.2 microns wide. So the adhesion between the gecko foot and the surface is exactly the result of a van der Waals force between each setae and the surface molecules. So if we estimate the total number to be about 3 million setae on a gecko's 2 feet, we can actually look at the intermolecular potential from this equation, and we can calculate that this is the force that we are able to calculate or see empirically on the gecko. So scientists have recreated gecko-like adhesion using silicons, plastics, carbon nanotubes, and other materials. So again, we look at silicones like PDMS to do this work, and I think there's examples in this presentation, or there's examples in other presentations I give of this man-made material. So synthetic setae emulate the setae found on the toes of the gecko, and in scientific research in this area is driven towards the development of dry adhesives. Potentially, adhesives could have many medical applications. For example, tapes that could replace sutures to close a wound, and water-resistant adhesions for bandages and drug delivery patches. So this is what gecko tape looks like. It's about 400 nanometers wide, created from silicone pillars, coated with muscle mimic polymer. So this is the schematic drawing of that. So you can take a look at this, maybe freeze the PowerPoint here or the video and take a look at this diagram. So we form the PMMA on silicon, and then we do a release on here. We then use our mold and pour PDMS on there. Then our PDMS becomes our gecko-like foot, and then we're able to actually recoat that with an additional polymer coating on the top to make this stuff tremendously strong. So this shows a mussel shell, seashell, and this is where material like super glue comes from, or I'm told that's the development of super glue, are these mussels or barnacles that attach to ships quite often. So silicone pillars are fabricated by electron beam lithography and coated with a synthetic form of the amino acid that naturally occurs in mussels. The material depends on van der Waals forces for its adhesive properties, and also on the chemical interaction of the surface with the hydroxyl groups in the mussel proteins. This material improves wet adhesion 15-fold compared to uncoated pillar arrays. This tape adheres through 1,000 contacts and release cycles, and it's sticky enough both in the wet and dry environments. So one of the first gecko tapes was formed of flexible fibers of polyamide as a synthetic setae structure on the surface of a 5-micron film. Fibers were 2 microns long with a diameter around 500 nanometers with a periodicity of about 1.6 microns. the tape's adhesion power increased almost 1,000 times if they used a soft bonding substrate such as Scotch tape, which allowed more contact to the surface. So this is a gecko tape, and we can see that this is this polymer is formed with e-beam lithography and dry etch in an oxygen plasma. And often what happens in an oxygen plasma for some polymers, what it's going to do is, I guess, uncover or elicit more bonds, free bonds at the surface to give us that adhesion. So this is a FESEM view of that. So I'd like to end here. That was our discussion of the principles of contact adhesion, material internal forces of copying nature, looking at the gecko foot, and how as engineers we could mimic that with synthetic materials. And I think it's interesting that we look at these, processes and also those materials in detail within this program. So those things are, as they say in the U.S., right in our wheelhouse, like in baseball kind of stuff. We can hit a home run with it. So I'd like to thank you for your attention and look forward to our further discussion. The next recording, what we're going to do in part 3 is look at the contact angle measurement. All right, guys, take care.